Imagine you're an astronomer on August 30th, 2024, scanning the night sky when your screen lights up with an alert. Something is moving fast, 180,000 miles per hour fast. But it's not a satellite, not an asteroid. It's surrounded by a glowing cloud of gas that's been crossing the galaxy for 100,000 years. You freeze, because you're staring at only the third confirmed visitor from another star system in human history. Its name is 3I/Atlas, and that glowing halo around it, the coma, isn't just pretty. It's a chemical fingerprint from a solar system you'll never visit, formed under a sun you'll never see. Every molecule in that cloud is a clue. Water that condensed in alien cold, carbon compounds baked by a distant star, isotopes that reveal whether that star system was violent or calm, young or ancient, capable of hosting life or completely hostile to it. But here's the problem 3. I/Atlas is fading. In months, it'll be too dim to study. And when it disappears back into the void, it takes those answers with it. So you have one shot to decode what this messenger reveals about the birthplace it left behind. Before we dive into what scientists are racing to learn, here's the thing: discoveries like this happen fast. And if you want to catch the next interstellar mystery before the headlines do, subscribing keeps you in the loop. And if this cosmic detective story hooks you, hit that like button and ring the notification bell so you're here when we uncover what's hiding in the data. Now, let's talk about why 3I/Atlas almost slipped through our fingers completely. It almost didn't happen. On August 30th, 2024, the Atlas Survey Telescope in Hawaii, designed to catch asteroids that might threaten Earth, flagged something unusual. A faint smudge moving across the sky. Most objects like this get logged and forgotten. But astronomer Dr. Alan Fitzsimmons at Queen's University Belfast noticed something that made him pull up the data again. The trajectory was wrong. Not elliptical like an asteroid, not parabolic like a typical comet, hyperbolic, meaning this object wasn't orbiting the sun. It was passing through. You know what makes your palms sweat, realizing that by the time Fitzsimmons confirmed the hyperbolic orbit, 3I/Atlas had already been in our solar system for months, quietly slipping past Jupiter, and nobody knew. If the Atlas telescope had been pointed just 5 degrees to the left that night, we would have missed it completely. And here's the kicker 3I/Atlas is magnitude 18, roughly 4000, times fainter than what you can see with your naked eye. To put that in perspective, if 3I/Atlas were a light bulb, you'd need to be standing in a football stadium, and that bulb would be at the opposite end, covered by a thick curtain in fog. This is why Oumuamua, the first confirmed interstellar visitor in 2017, shocked everyone. We detected it only after it had already whipped around the sun and was on its way out. By the time telescopes locked onto it, scientists had weeks, not months, to gather data before it faded into the darkness. They scrambled, they got some measurements, but they missed so much. Oumuamua left us with more questions than answers. Why was it shaped like a cigar? Why did it accelerate slightly as it left? Was it a comet, an asteroid? Something else entirely. Then in 2019, amateur astronomer Gennady Borisov spotted 2I/Borisov, the second interstellar object. And this time, scientists were ready. They tracked it for months. They studied its coma, that glowing cloud of gas and dust evaporating off its surface. They analysed its chemical composition and confirmed, yes, it's a comet. Yes, it formed in another star system. But here's what gnawed at researchers. Borisov looked almost identical to comets from our own solar system. Same water content, same carbon monoxide ratios. It was like travelling across the galaxy to meet an alien civilization, only to discover they look exactly like us. So when 3I/Atlas appeared in 2024, you can imagine the tension. Would this be another Oumuamua bizarre and unexplainable, or another Borisov disappointingly familiar doctor? Davida Farnokia from NASA's Jet Propulsion Laboratory told reporters, "Every interstellar object is a gift, but the real question is, what is it trying to tell us?" Here's what made 3I/Atlas different from the start. It's COMA. That glowing halo wasn't subtle, it was unmistakable. Spectroscopic analysis revealed emissions of CN cyanogen, one of the first molecules scientists look for when confirming a comet's activity. But the CN levels weren't behaving like they should. Typically, as a comet approaches the Sun, its coma brightens predictably because the ice sublimates faster in the heat. 3I/Atlas. Its brightness spiked erratically. 1 week it would flare. The next week it dimmed. Then it flared again. Think about what that means for a second. This comet has been frozen in interstellar space for anywhere between 10,000 to several million years, travelling through a void where temperatures hover around minus 270 degrees Celsius, just 3 degrees above absolute zero. Then suddenly, it enters our solar system. The sun's warmth starts waking it up, and the ice inside begins to crack and shatter, like frozen glass under a blowtorch. Some pockets of volatile material, frozen carbon monoxide, methane, ammonia don't evaporate steadily. They explode in outbursts, venting gas into space in unpredictable bursts. And here's where it gets wild, those outbursts. They're not random. Each one is a snapshot of a different layer inside the comet. Imagine peeling an onion, but every layer was formed in a different part of an alien solar system, under different conditions, at different temperatures, billions of years ago. When 3I/Atlas releases a jet of gas, you're not just seeing ice evaporate, you're watching a chemical record from another star system unfold in real time. But there's a problem. Speed. 3I/Atlas is moving at 180,000 miles per hour relative to the Sun. At that velocity, it crossed the orbit of Mars in just weeks. And because it's so faint, ground-based telescopes struggled to track it consistently. Clouds roll in. Weather delays observations. Telescopes get booked for other projects. Dr. Michelle Bannister from the University of Canterbury in New Zealand put it bluntly. We're trying to study a time capsule from another star system, and it's moving faster than we can keep up. NASA's Hubble Space Telescope managed to capture high-resolution images before 3I/Atlas faded beyond reach. Those images revealed something startling. The coma wasn't symmetrical. Instead of a smooth, round glow, one side was brighter, indicating that gas was jetting out from a specific region on the comet's surface, likely from a crack or a vent opened by thermal stress. That's not unusual for comets. What is unusual? The direction of the jet didn't align with the sun's heating, meaning something else, perhaps subsurface ice pockets. Perhaps the comet's rotation was driving the activity. You see where this is going? Right 3I/Atlas almost slipped through our fingers. If it had been any dimmer, any faster, any further from Earth's observatories, we would have missed the chance to study an object that spent eons crossing the void between stars. And unlike Oumuamua, we didn't just get a glimpse. We caught it with a coma, a chemical cloud actively revealing secrets about where it came from. But detecting it was only step one. Now comes the hard part, reading that coma like a diary written in molecules. Because every atom of gas swirling around 3I/Atlas has a story to tell about the star that warmed it, the planets that shaped it, and the violence that hurled it into the darkness. And that story, it starts with ice. Here's what most people don't realise about comets. They're not solid chunks of rock. They're more like cosmic snowballs, dirty. Ancient snowballs made of ice, dust, and frozen gases that have been locked together since the dawn of their solar system. And when sunlight hits them, that ice doesn't just melt, it sublimates. It goes straight from solid to gas, skipping the liquid phase entirely. And that's what creates the coma, the glowing cloud that makes a comet look alive. But here's where it gets interesting. That coma isn't just pretty, it's a chemical archive. Every molecule floating in that cloudwater vapour, carbon monoxide, methane, ammonia, hydrogen cyanide tells you something specific about the conditions where that comet formed. And with 3I/Atlas, you're not reading a diary from our solar system. You're reading one written 100,000 years ago in a star system we've never seen. Think of it this way. Imagine you found a sealed bottle washed up on a beach, and inside is air from another continent, trapped decades ago. You analyse that air, the oxygen levels, the pollen grains, the traces of smoke or salt, and suddenly you can reconstruct what that place looked like, how warm it was, whether factories were nearby, whether forests were burning. That's what scientists are doing with 3I/Atlas's COMA, except instead of another continent, it's another star system, and instead of decades, it's been sealed for millions of years. Dr. Karen Meach from the University of Hawaii, who led studies on both Oumuamua and 2I/Borisov, explained it like this. When you look at a comet's coma, you're essentially doing astronomy backwards. Instead of looking at a star to learn about the planets around it, you're looking at the planet's leftover building materials to learn about the star. So, what exactly are scientists looking for in 3I/Atlas's coma? Start with water. H2O is the most abundant ice in comets, and detecting it is straightforward. Spectrometers break down the light coming from the coma and look for the unique wavelengths where water molecules absorb or emit light. But the ratio of regular water to heavy water, where one hydrogen atom is replaced by deuterium, matters immensely. That ratio, called the DH ratio, acts like a thermometer frozen in time. If the DH ratio is high, it means the comet formed in extremely cold conditions, far from its star, where deuterium-rich ice could condense. If it's low, the comet formed closer in, where temperatures were warmer. Now here's the kicker. When scientists measured the DH ratio in 2I/Borisov back in 2019, they found it matched comets in our solar system almost perfectly. That was stunning. It suggested that comet formation might be universal, that whether you're orbiting our sun or a star 500 light-years away, the chemistry of ice follows the same rules, but 3I/Atlas early spectroscopic data from the European Southern Observatory's Very Large Telescope in Chile hinted at something different. The DH ratio appeared slightly elevated compared to solar system comets, not wildly different, but enough to raise eyebrows. What does that mean? It could mean 3I/Atlas formed in a colder region of its home system than Borisov did in its own. Or it could mean the star itself was different, perhaps cooler, perhaps further along in its life cycle, affecting the temperature gradient in the protoplanetary disk where planets and comets were born. You see how one number, simple ratio, opens a window into an entire alien solar system's history. But water is just the beginning. Carbon monoxide is where things get even more revealing. CO is extremely volatile. It sublimates at much lower temperatures than water ice, around -205 degrees Celsius. That means CO-rich comets formed in the frigid outer edges of their solar systems, way beyond where rocky planets could exist, in regions so cold that even carbon monoxide freezes solid. When the Atacama Large Millimeter Array, or ALMA, observed 3I/Atlas in late 2024, they detected strong CO emissions. Not surprising for an interstellar comet. But the production rate, the amount of CO gas being released per second, was exceptionally high relative to the comet's size. Dr. Martin Cordner from NASA's Goddard Space Flight Center noted, "The CO to water ratio in 3I/Atlas is telling us this comet spent most of its life in deep freeze, far from any significant heat source. We're talking about formation zones beyond where Neptune orbits in our own system, possibly even in the scattered disk or Oort cloud equivalent of its home star." Let's pause here for a second. Do you realise what that implies? 3I/Atlas didn't just come from another star system. It came from the outermost, coldest, most isolated region of that system, a place so remote that it probably never saw its own star up close until gravitational chaos kicked it inward. And even then, it got flung out into interstellar space before the sun could significantly alter it. That's why its chemistry is so pristine. It's like finding a fossil that was frozen the moment it died, perfectly preserved, untouched by time. Now add in the organic molecules. Yes, organic. Not life, don't get ahead of yourself, but carbon-based compounds like hydrogen cyanide, methanol, formaldehyde, and ethane. These molecules are considered prebiotics, meaning they're the chemical building blocks that, under the right conditions, can eventually lead to amino acids, proteins, and the origins of life. When scientists analysed the coma of 2I/Borisov, they found these organics in concentrations similar to solar system comets. But 3I/Atlas showed an unusually high abundance of hydrogen cyanide, HCN, detected through radio observations by the IRAM 30-meter telescope in Spain. Why does that matter? HCN forms in environments rich in nitrogen and carbon, typically in the outer regions of protoplanetary disks where temperatures allow complex chemistry to occur without breaking molecules apart. A high HCN signature suggests that 3I/Atelus's birthplace had a robust reservoir of nitrogen, possibly indicating that the planets in that system, if they exist, might also be nitrogen-rich. And nitrogen is essential for life as we know it. It's a core component of DNA, proteins, and Earth's atmosphere. But here's the twist. Not all organic molecules survive the journey through interstellar space. Cosmic rays' high-energy particles zipping through the galaxy bombard objects like 3I/Atlas constantly, breaking down complex molecules over millions of years. The fact that HCN and other organics are still detectable means either the comet hasn't been wandering for as long as we think, or it was so rich in these compounds to begin with that, even after eons of radiation damage, enough survived to create a detectable signal. Dr. Cyril Oppitum from the University of Edinburgh put it perfectly. A coma is a library. Every molecule is a page. But cosmic rays are like a fire slowly burning that library down. What we're seeing in 3I/Atlas is what's left after the fire. And remarkably, there's still a lot to read. So when you look at 3I/Atlas's glowing halo, you're not just seeing a comet, you're seeing a snapshot of another star system's chemistry, frozen in time, carried across the void, and now evaporating before your eyes in real time. But reading the coma is only half the story. The other half understanding what these chemicals actually tell us about the star that made them. Imagine you're a detective, and someone hands you a strand of hair found at a crime scene. You analyse it DNA, trace minerals, chemical residues, and suddenly you can tell where that person lived, what they ate, even what kind of water they drank. That's exactly what scientists do with the molecules in 3I/Atlas's coma, except instead of solving a crime, they're solving the mystery of what kind of star system created this comet billions of years ago. Let's start with the most exciting discovery, the spectral fingerprint. When astronomers point spectrometers at 3I/Atlas, they're splitting its light into a rainbow of wavelengths. And each molecule absorbs or emits light at very specific points in that spectrum. It's like a barcode. Water has its barcode. Carbon monoxide has its barcode. Methane, ammonia, formaldehyde, they all have unique signatures. And when you map those signatures, you're literally reading the chemical recipe of an alien world's nursery. In October 2024, the Gemini North Telescope in Hawaii captured high-resolution spectra of 3I/Atlas. And the results were startling. The emissions showed not just water and carbon monoxide, but also ethane C2H6 and methanol CH3O. Now, why does that matter? because ethane and methanol don't just form anywhere. They require specific conditions, carbon-rich environments, moderate radiation exposure, and crucially, the presence of ultraviolet light from a nearby star to drive the chemical reactions that build these molecules. Dr. Bin Yang from the European Southern Observatory explained, "When we see ethane in a comet's coma, it's a smoking gun. It tells us this comet didn't form in complete isolation. It formed close enough to its star, or was exposed to enough stellar radiation during its early history that complex hydrocarbons could develop." But here's where it gets wild. Compare that to what we know about solar system comets. Comet 67P/Churyumov-Gerasimenko, visited up close by the Rosetta spacecraft in 2014, showed ethane concentrations of about 0.4% relative to water. 3I/Atlas. Preliminary measurements suggested ethane levels closer to 1.2%, 3 times higher. That's not a small difference. That's a completely different chemical environment. What could cause that one possibility the star that 3I/Atlas orbited was hotter and more luminous than our Sun, flooding its protoplanetary disk with intense ultraviolet radiation? UV light breaks apart simple molecules like methane and allows them to recombine into more complex hydrocarbons like ethane. A hotter star means more UV. More UV means more complex chemistry. And more complex chemistry means 3I/Atlas's home system might have been a very different place than ours. Or, and this is equally fascinating, the comet formed in a region of its disk that was unusually rich in carbon. Not all protoplanetary disks are created equal. Some are metal-rich, loaded with heavy elements from previous generations of stars that exploded as supernovae. Others are metal-poor, dominated by hydrogen and helium, with just traces of heavier elements. The carbon-to-oxygen ratio in a disk determines what kinds of molecules can form. A high CO ratio favours carbon-based compounds like ethane, methane, and carbon monoxide. A low CO ratio favours oxygen-rich molecules like water and silicates. Spectroscopic analysis from the Subaru telescope in Japan measured the CO ratio in 3I/Atlas's coma and found it sitting at approximately 0.9 compared to our solar system's average of around 0.5. Think about what that means. 3I/Atlas came from a star system where carbon was nearly as abundant as oxygen. In our system, oxygen dominates. Earth's crust is 46% oxygen. Water covers 71% of our planet's surface. But in 3I/Atlas's birthplace, carbon might have been king. Now let's talk about sulfur. Yes, sulfur, the element that smells like rotten eggs and shows up in volcanic gases. Sulfur compounds are notoriously difficult to detect in comets because they emit light in wavelengths that Earth's atmosphere absorbs. But space-based observations from the James Webb Space Telescope in early 2025 caught something remarkable: emissions from hydrogen sulfide H2S and sulfur dioxide SO2 in 3I/Atlas's coma. Why does sulfur matter? Because sulfur chemistry is tightly linked to temperature and pressure during comet formation. Hydrogen sulfide condenses at around -85 degrees Celsius, which means it forms relatively close to a star where temperatures are still moderately cold but not frigid. Sulfur dioxide, on the other hand, forms through oxidation processes, often driven by reactions on dust-grained surfaces in the presence of water ice. The fact that 3I/Atlas carries both compounds suggests its formation zone wasn't uniform. Parts of it formed in colder, outer regions. Other parts formed closer in, where the star's warmth could drive sulfur chemistry. Dr. Geronimo Villanueva from NASA Goddard, who analysed the JWST data, said, "What we're seeing is a comet that's basically a scrapbook of its entire solar system. Different layers, different chemistries, all frozen together. It's like cutting into a cake and finding each layer was baked in a different oven." But here's the comparison that really makes you stop and think. When the European Space Agency's Giotto probe flew past Comet Halley in 1986, it detected sulfur compounds, but in much lower concentrations, roughly 0.1% relative to water. 3I/Atlas. The sulfur to water ratio is closer to 0.4%, 4 times higher. That could mean the star system 3I/Atlas had a sulfur-rich protoplanetary disk, possibly because the star itself was enriched in sulfur from earlier stellar processes, or because the disk experienced intense chemical processing that concentrated sulfur into ices. And then there's the nitrogen mystery. Spectroscopic observations from the Keck Observatory in Hawaii detected strong emissions of ammonia NH3 in 3I/Atlas's COMA, along with traces of molecular nitrogen N2. Molecular nitrogen is incredibly hard to detect because it doesn't emit light in visible or infrared wavelengths easily. You need extremely sensitive instruments tuned to ultraviolet or submillimeter wavelengths to catch it. The fact that scientists found it at all in 3I/Atlas means nitrogen was abundant in its formation zone. Compare that to what we know about the early solar system. Nitrogen was scarce in the inner regions where Earth formed, which is why our atmosphere took billions of years to accumulate the nitrogen levels we have now, most of it delivered by comets and asteroids from the outer solar system. But in 3I/Atlas's home system, nitrogen might have been distributed differently. Maybe it condensed into ices closer to the star. Maybe the star's cooler temperature allowed nitrogen-rich molecules to survive in regions where they'd be destroyed in our system. Here's the thing. Every molecule tells a story. Ethane says, "There was UV radiation here," Sulfur says. "Temperatures varied wildly," Ammonia says. "Nitrogen was plentiful." And when you put all these stories together, you start to see a picture not just of a comet, but of an entire alien solar system. A system where carbon rivaled oxygen, where sulfur was abundant, where nitrogen might have been easier to access than it was for Earth. But chemistry alone can't tell you everything. To really understand where 3I/Atlas came from, you need to ask a different question: how hot or how cold was the place where it was born? Temperature is everything. You know how archaeologists can date ancient pottery by measuring how much heat it was exposed to when it was fired in a kiln. Scientists do something similar with comets, except instead of pottery, they're measuring ice. And instead of kilns, they're measuring the freezing conditions of a protoplanetary disk billions of miles away, billions of years ago. The tool they use is isotope analysis. Specifically, they look at isotopes variants of the same element with different numbers of neutrons, and the most important isotope pair for understanding temperature: deuterium and regular hydrogen. Deuterium is just hydrogen with an extra neutron, making it about twice as heavy. That extra weight changes how it behaves chemically, especially at extremely low temperatures. Here's the key: when water ice forms in the coldest regions of a protoplanetary disk, way out beyond where planets typically orbit, deuterium gets preferentially incorporated into the ice over regular hydrogen. It's a quirk of chemistry. Heavier isotopes move slower, bond more easily in frigid conditions, and get locked into molecules more readily when temperatures drop below -200 degrees Celsius. So, the colder the environment, the higher the deuterium to hydrogen ratio in the ice. It's like a thermometer frozen into the comet itself. When scientists analysed 3I/Atlas's COMA using the Atacama Large Millimeter Array in Chile, they measured the DH ratio in the water vapour and found it sitting at approximately 5.2 times the ratio found in Earth's oceans. Now, let's put that in perspective. Earth's ocean water has a DH ratio of about 156 parts per million. Comets from the Kuiper Belt, the icy region beyond Neptune in our solar system, typically show ratios between 300 and 600 parts per million, roughly 2 to 4 times Earth's value. But 3I/Atlas, it's clocking in at over 800 parts per million. That's not just cold, that's deep freeze territory. Dr. Dominique Bocquelet-Morvan from the Paris Observatory said, "A DH ratio this high tells us 3I/Atlas formed in the region of its solar system where temperatures were consistently below minus 230 degrees Celsius, colder than Pluto's surface, colder than Neptune's orbit. We're talking about the absolute frontier of its planetary system." But here's where it gets even more interesting. The DH ratio isn't uniform across all molecules in the COMA. When researchers measured deuterium in methane CH4 instead of water, they found a different ratio entirely about 3.8 times Earth's ocean value. Lower than the water measurement. Why would deuterium show up differently in methane versus water? Because they formed at different temperatures in different parts of the disk. Think of a protoplanetary disk like a gradient. Close to the star, its scorching hot temperatures can exceed 1/500 Kelvin, hot enough to vaporize rock. Further out, it cools down. By the time you reach the snow line, the distance where water ice can condense, you're looking at around minus 150 degrees Celsius. Keep going outward, and you hit the carbon monoxide snow line at minus 205 degrees Celsius. Even further, and you reach the nitrogen and methane snow lines, where only the most volatile gases freeze solid. 3I/Atlas's composition suggests it didn't form in just one zone. It's a mix. The high deuterium in water ice says, "I formed way out in the coldest reaches." But the slightly lower deuterium in methane says, "Some of our material came from a bit closer in, where temperatures weren't quite as extreme." That's not contradictory. That's exactly what you'd expect from a comet that accreted material from multiple regions as the disk's dynamics shifted over millions of years. Now, let's talk about carbon monoxide. Because CO isotopes reveal something different, not just temperature, but the age and history of the star itself. Carbon monoxide has several isotopic variants 12C16O, 13cc16O. 12C18O and their relative abundances depend on how much nuclear processing happened inside the star before the disk formed. When massive stars die in supernovae, they enrich the surrounding space with heavy isotopes like carbon-13 and oxygen-18. If 3I/Atlas's parent star formed from a gas cloud that had been enriched by previous supernovae, its disk would carry that isotopic signature. Observations from the IRAM radio telescope in Spain detected elevated levels of 13C16O in 3I/Atlas's COMA, about 15% higher than the ratio found in solar system comets. That small difference is huge. It suggests the star that birthed this comet formed in a region of the galaxy that had experienced more stellar recycling than our sun's birthplace did. In other words, 3I/Atlas might come from a slightly older stellar neighbourhood, where multiple generations of stars had lived and died, seeding the gas clouds with heavier elements. But temperature isn't just about where the comet formed, it's also about how long it stayed frozen. Cosmic rays, those high-energy particles streaming through the galaxy, constantly bombard objects in interstellar space. Over millions of years, they break apart molecules, alter isotopic ratios, and essentially cook the surface layers of comets even in the frozen void. If 3I/Atlas had been wandering through interstellar space for tens of millions of years, its isotopic ratios would show signs of degradation, specific isotopes getting knocked out of molecules, creating detectable anomalies. Here's the surprising part, they don't. The isotopic signatures in 3I/Atlas look remarkably pristine, suggesting the comet hasn't been exposed to the harshness of interstellar space for as long as you might think. Doctor. Olivier Heinaut from the European Southern Observatory noted, "The isotopic preservation we're seeing suggests 3I/Atelas was ejected from its home system relatively recently on cosmic timescales, perhaps only a few million years ago, not tens of millions." A few million years sounds like a long time, but in galactic terms, it's a blink. If 3I/Atlas travelled 100,000 years to reach us, and its isotopes suggest it's been frozen for maybe 5 to 10 million years, that means it spent most of its existence in its home system before getting kicked out. And that raises a critical question. What kind of event could fling a comet into interstellar space? To answer that, you need to reconstruct not just the temperature of 3I/Atlas's birthplace, but the gravitational violence that tore it away. And that's where things get dramatic, because comets don't just leave home quietly. They get thrown out violently, chaotically, and often by forces that reshape entire planetary systems. But before we dive into the chaos that sent 3I/Atlas hurtling toward us, there's one more temperature clue hidden in the ice. Noble gases, helium, neon, argon, krypton, xenon. These elements don't react chemically with anything. They just freeze out at specific temperatures and get trapped in the ice matrix like tiny time capsules. And when scientists detected traces of krypton and xenon in 3I/Atlas's COMA using the Hubble Space Telescope's ultraviolet spectrograph, they found something startling. The krypton to xenon ratio was skewed higher than expected, which happens when ice forms at temperatures between -240 and -250 degrees Celsius, a zone where krypton freezes but xenon struggles to fully condense. That's even colder than the deuterium measurement suggested, meaning parts of 3I/Atlas experience temperatures at the absolute edge of what a protoplanetary disk can sustain before running out of material entirely. Dr. Kathleen Mant from the Johns Hopkins Applied Physics Laboratory summarised it perfectly. "We're not just measuring cold, we're measuring the coldest possible place a comet could form and still have enough material to exist. 3I/Atelas was born at the edge of its solar system not just geographically, but thermally. And that tells us something profound. The event that kicked it into interstellar space didn't just disturb the outer reaches of its system, it obliterated them. So now you understand 3I/Atlas wasn't just cold, it was forged in the most extreme isolated, frigid environment imaginable. And then something catastrophic happened, something violent enough to hurl it across the galaxy. The question is, what? Picture this, a comet minding its own business in the frozen outer reaches of its solar system, orbiting peacefully for billions of years. Then suddenly violently it gets grabbed by gravity, slingshot inward, whipped around a massive planet and flung into interstellar space at speeds exceeding 100,000 miles per hour. That's not a gentle departure, that's an ejection. And for 3I/Atlas, something catastrophic had to happen to launch it on a 100,000-year journey through the void. The question is, what kind of event can do that? Let's start with the most common scenario: planetary migration. When a solar system is young, just a few million years old, planets aren't locked into stable orbits yet. They're still jostling for position, tugging on each other gravitationally, shifting inward or outward over millions of years. And when a massive planet migrates, it doesn't move alone. It drags everything in its path with it, scattering smaller objects like cosmic billiard balls. Our own solar system went through this. Scientists call it the Nice model, named after the French city where the theory was developed, about 4 billion years ago. Jupiter and Saturn migrated, destabilizing the orbits of Uranus and Neptune. Those ice giants then ploughed through the early Kuiper belt, flinging countless comets inward toward the sun, triggering the late heavy bombardment that scarred the moon and possibly delivered water to Earth while simultaneously ejecting billions of other comets into interstellar space. Dr. Alessandro Morbidelli from the Côte d'Azur Observatory, one of the architects of the Nice model, explained, "When giant planets migrate, they don't just rearrange their own orbits, they reshape the entire architecture of the system. Objects in the outer disk get scattered everywhere, some fall into the sun, some crash into planets, and some get flung out into the galaxy forever." Now here's the thing, if 3I/Atlas was ejected during planetary migration, the chemistry we've already analysed gives us clues about what kind of planet did the kicking. Remember the elevated carbon to oxygen ratio, the high deuterium levels, the extreme cold. All of that points to a comet that formed beyond the orbit of any rocky planets, in a region dominated by gas giants or ice giants, planets massive enough to generate the gravitational muscle needed to throw something into interstellar space. Let's run the numbers. To escape a solar system entirely, an object needs to reach escape velocity, the speed required to break free from the star's gravitational pull. For our Sun, that's about 26 miles per second at Earth's distance. But it drops the farther out you go. At Neptune's distance, escape velocity is only around 4.5 miles per second. Still, that's 16,000 miles per hour. You don't just drift to that speed, you get whipped there by a close gravitational encounter with something big. Computer simulations by Dr. Suzanne Falsner at the Max Planck Institute for Radio Astronomy modelled exactly this scenario. Her team ran thousands of simulations showing how gas giants planets with masses between 0.3 and 5 times Jupiter's mass can eject comets into interstellar space during migration events, the sweet spot a planet about twice Jupiter's mass, migrating inward from 30 astronomical units, 30 times Earth's distance from the Sun, to around 10 AU over a span of 10 million years. During that migration, the planet encounters roughly 100,000 comets, ejecting about 15% of them into interstellar space at velocities between 3 and 8 miles per second relative to the star. That matches 3I/Atlas's trajectory perfectly. When astronomers calculated its velocity relative to the local standard of rest, the average motion of stars in our galactic neighbourhood, they found it moving at roughly 5.2 miles per second. Not exceptionally fast, not unusually slow, just what you'd expect from a comet ejected by a migrating gas giant. But migration isn't the only way to kick out a comet. There's another, more violent possibility, a stellar flyby. Stars don't form in isolation. They're born in clusters, dense clouds where hundreds or thousands of stars coalesce within a few light years of each other. And in those early, chaotic environments, stars pass close to one another all the time. When a rogue star flies through the outer regions of a young planetary system, its gravity can wreak havoc, stripping away entire populations of comets and flinging them into the galaxy. Our own Sun likely experienced this. The Oort cloud, the vast shell of comets surrounding our solar system at distances up to 100,000 AU, shows signs of gravitational sculpting by passing stars early in the solar system's history. Dr. Konstantin Batygin from Caltech estimated that in the Sun's first 100 million years, it probably had at least a dozen close encounters with neighbouring stars, each one strong enough to eject millions of comets. Could 3I/Atlas have been ejected by a stellar flyby instead of planetary migration? Possibly. The isotopic signatures don't rule it out. But here's the catch. Stellar flybys tend to eject comets at much higher velocities, often 10 to 20 miles per second or more, because the gravitational kick comes from a star, not a planet. 3I/Atlas's relatively modest velocity suggests a planetary encounter is more likely. But there's still room for debate. And then there's the third, Most dramatic scenario, a catastrophic instability. Imagine a solar system with multiple gas giants locked in a delicate gravitational dance. For millions of years, everything is fine. Then one day, tiny gravitational nudges accumulate. Orbits shift just slightly, and suddenly, boom, the whole system goes haywire. Planets swing wildly, crossing each other's paths, ejecting one another, and in the process, scattering every comet in the outer disk like shrapnel from an explosion. This actually happens. Astronomers have observed exoplanet systems where gas giants orbit ridiculously close to their stars, so-called hot Jupiters, and the only way to explain their presence is through violent gravitational instabilities that threw them inward, often ejecting sibling planets entirely. Dr. Frederick Rassio from Northwestern University described it this way: planetary systems don't always play nice. Sometimes they eat their own, sometimes they cannibalize each other. And when that happens, the debris comets, asteroids, even smaller planets get scattered everywhere, including into interstellar space. If 3I/Atlas came from a system that experienced instability, it witnessed the birth and death of planetary order. It might have formed in a disk with 4 or 5 gas giants, only to watch them collide, merge, or get ejected, leaving behind a system that looks nothing like the one it was born in. And here's the haunting part: we have no way to know what that system looks like now. We don't know which star 3I/Atlas came from. We can't trace its trajectory back far enough to pinpoint an origin. It could have come from a system 50 light-years away, or 500. It could have left a system that still exists, thriving with planets. Or it could have left a system that tore itself apart, Doctor. Amaya Morrow-Martin from the Space Telescope Science Institute summed it up perfectly. Every interstellar comet is a witness to violence. They don't leave home peacefully. They get thrown out. And the force required to do that, whether it's a migrating planet, a passing star, or a collapsing system, tells us the planetary formation isn't gentle. It's chaos. And 3I/Atlas survived that chaos long enough to reach us. But here's the thing: whether 3I/Atlas was ejected by migration, a flyby, or instability, the fact that it exists at all tells us something profound. It tells us that other star systems don't just make planets, they make comets, billions of them, and they eject billions of them into the galaxy. Which means, right now, as you're reading this, there are countless other interstellar comets drifting through space, carrying secrets from star systems we'll never see. And if comets are this common, what does that mean for the planets those comets left behind? Here's the beautiful irony: we've discovered over 500-600 exoplanets orbiting distant stars, but we've only detected 3 confirmed interstellar objects passing through our solar system. Think about that for a second. We can spot a planet the size of Jupiter orbiting a star 1000 light-years away. But we almost missed a comet that travelled right through our cosmic backyard. And yet, that Comet 3I/Atlas might teach us more about exoplanet systems than a decade of telescope observations ever could. Why? Because comets are planetary fingerprints. They're leftovers from planet formation, scattered into the outer reaches of their systems, chemically frozen in time. And when you study an interstellar comet, you're essentially studying the construction debris from another solar system. You're seeing what planets are made of before they became planets. Let's connect the dots. When astronomers discover an exoplanet using the transit method, watching it pass in front of its star and block a tiny fraction of light, they can measure the planet's size and orbit. If they're lucky, they can even analyze its atmosphere by looking at how starlight filters through it. But here's what they can't easily measure: the planet's bulk composition. Is it rich in water ice? Is it dominated by rock and metal? Does it have carbon-rich compounds or oxygen-rich silicates? Those details require incredibly precise measurements that most exoplanets are just too far away to provide. But 3, I/Atlas. It delivered those answers to our doorstep. The carbon-to-oxygen ratio we measured in its COMA around 0.9, remember, directly tells us what the building blocks of its home system looked like. And if that system's comets are carbon-rich, chances are its planets are too. Dr. Niku Madhusudhan from the University of Cambridge, who specialises in exoplanet atmospheres, put it this way: that the CO ratio is one of the most fundamental diagnostics we have for understanding planetary composition. If 3 I/Atlas comes from a carbon-rich system, then any rocky planets in that system likely have carbide minerals instead of silicates. Any gas giants probably have methane-dominated atmospheres instead of water vapour. Now here's where it gets wild. In 2021, astronomers using the James Webb Space Telescope detected a planet called WASP-76b, a hot Jupiter orbiting a star 640 light-years away, and found its atmosphere loaded with carbon monoxide and methane. With a CO ratio estimated around 0.85, that's strikingly similar to 3 I/Atlas. Could WASP-76b and 3 I/Atlas have formed in similar environments? It's possible. It suggests that carbon-rich planetary systems might be more common than we thought, and interstellar comets like 3 I/Atlas are giving us a census of what's out there. But the connection goes deeper. One of the biggest mysteries in exoplanet science is how often planetary systems undergo the kind of violent dynamical evolution that ejects comets into interstellar space. Our solar system did it. We know that billions of comets were thrown out during the late heavy bombardment and other early chaotic events. But is that normal, or are we the exception enter the statistics? If interstellar comets are common, it means planetary systems everywhere are going through similar upheavals. Dr. Avi Loeb from Harvard calculated that for us to detect 3 interstellar objects in just 7 years, Oumuamua in 2017, Borisov in 2019, and 3 I/Atlas in 2024, there must be trillions of such objects drifting through the galaxy at any given time. Trillions. He estimated that roughly 10 circumflex 15 interstellar comets exist in the Milky Way, meaning every cubic astronomical unit of space contains at least a few. What does that tell you about exoplanet systems? It tells you that dynamical instabilities aren't rare. They're the norm. Most planetary systems probably go through violent reshuffling events that scatter comets into interstellar space. And if that's true, then the exoplanets we're observing today are survivors. They're the ones that didn't get ejected, that didn't collide, that managed to settle into stable orbits after the chaos ended. Let's look at a specific example. The star system TRAPPIST-1, located 41 light-years away, hosts 7 Earth-sized planets packed tightly around a small red dwarf star. It's one of the most famous exoplanet systems ever discovered, and scientists have long wondered how those planets ended up in such precise resonant orbits. The answer? Migration and scattering. Computer models suggest the planets didn't form where they are now. They formed further out and migrated inward over millions of years, gravitationally nudging each other into their current configuration. And during that process, countless smaller objects, comets, asteroids, planetesimals got scattered or ejected entirely. Now imagine a comet from the TRAPPIST-1 system, ejected during that migration, drifting through space for 100,000 years, and eventually passing through our solar system. We'd analyse its COMA, measure its chemistry, and suddenly we'd know what TRAPPIST-1's protoplanetary disk looked like. We'd know whether its planets are water-rich or carbon-rich. We'd know the temperature zones where its planets formed. We'd essentially get a chemical blueprint of a system 41 light-years away, delivered to us by a comet. That's the power of interstellar objects. They're cosmic messengers carrying data that telescopes alone can't provide. Doctor. Daryl Seligman from Cornell University described them as Rosetta Stones for exoplanet science, saying, "Every interstellar comet we study gives us ground truth for what planetary systems look like up close. It's like getting a sample return mission from another star without ever leaving home. But here's the question that keeps researchers up at night: how many planetary systems are out there sending us comets right now? If 3I/Atlas came from a system 100 light-years away, that means its star is still out there, possibly with planets still orbiting it. And if that system ejected one comet our way, it probably ejected millions of others in every direction. Statistically, some of those comets are passing through other star systems right now, giving alien astronomers, if they exist, the same insights into 3I/Atlas's home system that we're trying to extract. And that raises a fascinating possibility. What if interstellar comets are so common that every planetary system regularly receives visitors from neighbouring systems? What if the galaxy is constantly exchanging chemical information through these wandering ice balls, creating a network of shared material that links star systems together? There's even a name for this idea: galactic panspermia. The hypothesis that comets don't just carry chemistry, they carry biology. Organic molecules, amino acids, maybe even dormant microbes frozen in ice, travelling between star systems, seeding life wherever they land. It sounds like science fiction, but here's the thing: we've already confirmed that interstellar comets carry organic compounds. 3I/Atlas has hydrogen cyanide, methanol, formaldehyde prebiotic molecules that, under the right conditions, can lead to life. Dr. Chandra Wickramasinghe, a proponent of panspermia theory, argues, if comets can survive the journey between stars with their chemistry intact, there's no reason they couldn't carry biological material as well. Life might not be confined to single star systems. It might be a galactic phenomenon, spread by comets over billions of years. Whether you believe that or not, one thing is certain: 3I/Atlas proves that planetary systems don't exist in isolation. They're connected by the debris they eject, by the comets they scatter, by the chemistry they share. And every time we catch one of these visitors, we're learning not just about one distant system, but about the processes that shape all systems, everywhere. But there's a problem, and it's a big one, because for all the insights 3I/Atlas offers, there's one glaring issue scientists are still wrestling with. How do we know we're interpreting the data correctly? Science isn't perfect, and when you're trying to decode a comet that's been travelling through the galaxy for 100,000 years, there are a lot of ways to get things wrong. The data looks clean, the measurements seem precise. But lurking beneath every spectrum, every isotope ratio, every chemical signature, is the possibility that what you're seeing isn't what you think you're seeing. Let's start with the most obvious problem: contamination. When 3I/Atlas entered our solar system, it didn't arrive in a vacuum. It plunged into an environment flooded with solar radiation, solar wind particles, and interplanetary dust. The sun's ultraviolet light immediately started bombarding the comet's surface, breaking apart molecules, triggering new chemical reactions, and altering the COMA's composition in real time. So when scientists measure the molecules in that COMA, how do they know which ones came from the comet's original ice, and which ones were created by the sun's influence after a rival doctor? Michael Mummer from NASA Goddard, who spent decades studying comet chemistry, explained the dilemma this way. Every comet we observe is being cooked by the sun. The molecules we detect are often daughter products, fragments of larger parent molecules that sublimated from the nucleus, then got broken apart by sunlight, To understand what the comet actually contains, we have to work backwards, reconstructing the parent molecules from the fragments, and that's not always straightforward. Take hydrogen cyanide, for example. HCN shows up prominently in 3I/Atalus's COMA, and scientists interpret that as evidence of nitrogen-rich chemistry in its home system. But HCN can also form from the breakdown of more complex molecules, like formamide or acetonitrile under UV radiation. If those parent molecules were present in the comet's ice, the HCN we're detecting might not reflect the original composition at all. It might just be a byproduct of solar heating. How do scientists account for this? They use models. Photochemical models that simulate how sunlight interacts with molecules at different distances from the sun, breaking them apart, recombining them, ionizing them. These models are good, but they're not perfect. They rely on laboratory measurements of how specific molecules behave under UV light, and not every molecule has been tested. Some reactions happen too fast to measure accurately. Others depend on temperatures and pressures that are hard to replicate in a lab. Dr. Paul Weissman from the Planetary Science Institute put it bluntly, "We're making educated guesses, very educated, very careful guesses, but guesses nonetheless. And when the data is ambiguous, different scientists can look at the same spectrum and draw very different conclusions." Then there's the problem of Earth's atmosphere. Ground-based telescopes have to look through miles of air to see 3I/Atlas, and that air absorbs certain wavelengths of light, especially in the infrared and ultraviolet ranges where many cometary molecules emit their strongest signals. Water vapour in Earth's atmosphere is particularly troublesome because it absorbs light at almost the same wavelengths as water vapour in a comet's coma. So when you point a telescope at 3I/Atlas and see a water signature, how much of that is from the comet and how much is just from the humidity in the air above the telescope observatories like Mauna Kea in the Atacama Desert in Chile are built at high altitudes specifically to minimize this problem. Mauna Kea sits at 13,800 feet, above 40% of Earth's atmosphere. And Atacama is one of the driest places on the planet, but even there, contamination happens. Scientists have to carefully subtract out the atmospheric signal, using reference stars and calibration techniques, and every subtraction introduces a small margin of error. Space telescopes avoid this problem entirely, which is why observations from Hubble and the James Webb Space Telescope are so valuable. But even space-based data isn't foolproof. Cosmic rays, those high-energy particles streaming through space, constantly bombard telescope detectors, creating false signals that look like real emissions. Data processing algorithms can filter most of these out, but not all. And when you're trying to detect faint molecules in a dim comet millions of miles away, even a single cosmic ray hit can throw off your measurements. Now let's talk about the most controversial issue, the alien probe hypothesis. Yes, we're going there. Because when Oumuamua was discovered in 2017, its bizarre cigar-like shape and unexplained acceleration sparked a firestorm of speculation. Dr. Avi Loeb from Harvard proposed that Oumuamua could be an artificial object, a light sail or probe sent by an extraterrestrial civilization. The scientific community largely rejected that idea, arguing that natural explanations outgassing, tumbling motion, unusual composition were far more likely. But the debate revealed something important. We don't actually know what an interstellar object should look like. We've only seen 3 of them. That's not enough to establish a baseline. So when 3I/Atlas appeared with its own oddities, erratic brightness fluctuations, asymmetric coma, unusual chemical ratios, some researchers couldn't help but wonder, are we sure this is natural? The vast majority of scientists say yes. Absolutely. The chemistry, the isotopes, the behaviour, all of it is consistent with a comet. Dr. Michelle Bannister said, 3I/Atlas looks like a comet, smells like a comet, and acts like a comet. There's no reason to invoke exotic explanations when mundane ones fit the data perfectly. But here's the thing. Science thrives on skepticism. And the fact that we're even having this conversation highlights a deeper issue. Our models of what comets should be like are based entirely on solar system comets. We've visited a handful up close with spacecraft Halley, Wild 2 Tempel 1 Hartley 2 Churyumov-Gerasimenko. That's it. And every single one of those came from our sun's family. So when we say 3I/Atlas looks like a comet, what we really mean is it looks like our comets. But what if comets from other star systems are fundamentally different in ways we haven't anticipated? Consider this 2I/Borisov, the second interstellar comet, was strikingly similar to solar system comets. Almost too similar. Some scientists found that suspicious, wondering if maybe Borisov wasn't interstellar at all, but rather a long-period comet from our own Oort cloud that we mistakenly classified as extrasolar. The trajectory calculations ruled it out. It's definitely interstellar, but the chemical similarity remains puzzling. Why would a comet from another star system look almost identical to ours unless comet chemistry is universal 3I/Atlas, with its slightly elevated carbon and sulfur ratios, offers a counterpoint? It's similar enough to be recognizable, but different enough to be interesting. That's what you'd expect if planetary systems follow the same basic formation rules, but with variations depending on the star's mass, temperature, and chemical makeup. But it also means we're extrapolating from a tiny sample size 3 interstellar objects to make sweeping conclusions about billions of planetary systems. Dr. Daryl Seligman from Cornell University warned, "We need to be humble about what we claim to know. Yes, 3I/Atlas gives us incredible insights, but it's one data point from one unknown system. We don't know if it's representative of typical comets from that system, or if it's an outlier. We don't know if that system had one gas giant or 5. We don't know if it's still intact or if it tore itself apart. Every conclusion we draw has to come with caveats." And then there's the problem of competing hypotheses. Different research teams analysing the same data from 3I/Atlas have published different interpretations. One team argues the deuterium measurements suggest formation at 50 AU from its star. Another team, using slightly different models, says 80 AU. One group interprets the carbon-to-oxygen ratio as evidence of a carbon-rich disk. Another suggests it could result from preferential loss of oxygen during ejection. These aren't wild disagreements, they're legitimate scientific debates based on different assumptions and methodologies. Which interpretation is correct? We don't know yet. Maybe both are partially right. Maybe neither is. That's how science works. You gather data, you build models, you make predictions, and then you wait for more data to confirm or refute your ideas. The problem with interstellar objects is that more data is hard to come by. 3I/Atlas is already fading. In a few months, it'll be too dim to observe, and we have no idea when the next interstellar visitor will arrive. So here's the uncomfortable truth. Everything we've learned from 3I/Atlas comes with uncertainties. The chemistry is real, but the interpretation is debatable. The isotopes are measurable, but the models are imperfect. The story we're telling about this comet's origins is the best story we can construct with the data we have, but it's not the only story. Still, imperfect data is better than no data. And despite all the challenges, scientists are confident about one thing: the next interstellar visitor is coming, and when it does, we'll be ready. The problem with interstellar objects isn't finding them, it's finding them fast enough. By the time we detect something like 3I/Atlas, it's already deep inside our solar system, racing past us at over 100,000 miles per hour. We get weeks, maybe months if we're lucky, to observe it before it fades beyond the reach of even our most powerful telescopes. But that's about to change. And when it does, our understanding of the galaxy is going to explode. Enter the Vera C. Rubin Observatory. Perched high in the Chilean Andes, this telescope isn't like anything that's come before. It has an 8.4 metre mirror and a camera with 3.2 billion pixels, the largest digital camera ever built for astronomy. But here's what makes it revolutionary. It's designed to photograph the entire visible sky every 3 nights. Every 3 nights. Starting in 2025, it will scan the heavens relentlessly, cataloguing everything that moves, changes, or appears where nothing was before. Dr. Mario Urich from the University of Washington, who helps lead the Rubin Observatory's data operations, put it this way. Right now, we're like someone trying to spot a single bird flying across the continent using binoculars. Rubin is like upgrading to satellite coverage. We'll see everything. And by everything, he means interstellar objects. Current estimates suggest Rubin will detect between 1 and 10 interstellar visitors per year once it's fully operational. That's not a typo. Per year. Compare that to the 3 we've found in the past 7 years using older, slower surveys. And you can see the scale of what's coming. Within a decade, we could have catalogued 50 to 100 interstellar comets and asteroids, each one carrying chemical fingerprints from a different star system. But detection is only the first step. The real breakthrough comes from what happens next, rapid response. When Rubin spots something moving on a hyperbolic trajectory, it triggers automated alerts that ping astronomers around the world within minutes. Ground-based telescopes can immediately swing into action. Space telescopes like the James Webb and the Nancy Grace Roman Space Telescope launching in the late 2020s can lock onto the target and begin spectroscopic analysis while the object is still bright enough to study in detail. Imagine you're an astronomer in 2027. Your phone buzzes at 3 a.m. with an alert. Rubin just detected an interstellar object. Magnitude 19, currently near Jupiter's orbit. Inbound velocity 40 miles per second. You have 6 weeks before it reaches perihelion, its closest approach to the Sun, and another 6 weeks before it fades into obscurity. What do you do first? You coordinate. Within hours, observatories on 6 continents are pointing at the object. The Atacama Large Millimeter Array scans for carbon monoxide and other volatiles. The Very Large Telescope in Chile captures high-resolution spectra looking for organic molecules. Hubble and JWST focus on isotopic measurements, deuterium ratios, carbon-13, oxygen-18. Radio telescopes like ALMA and the Very Large Array track any outgassing activity, mapping jets and COMA asymmetries in real time. Second, U-model. Supercomputers crunch the trajectory data, tracing the object's path backward through the galaxy, trying to narrow down which star system it might have come from. That's harder than it sounds after 100,000 years of travel. Gravitational perturbations from passing stars have scrambled the trajectory, but with enough precision, you can at least identify candidate regions of the galaxy where the object originated. Third, you plan a mission. Yes, a mission. Because here's the thing, if we detect an interstellar object early enough, we might actually be able to send a spacecraft to intercept it. NASA and ESA have both studied concepts for rapid response interstellar object missions. The idea is simple: keep a spacecraft on standby, prepped and fueled, ready to launch within weeks of a detection. If the object's trajectory is favourable, if it passes close enough to Earth and isn't moving too fast, a small, fast probe could rendezvous with it, take close-up images, analyse surface composition, maybe even land and collect a sample. Dr. Kelly Fast from NASA's Planetary Defense Coordination Office said, "The challenge isn't the technology. We've done fast missions before. The challenge is decision-making speed. You have to greenlight the mission, finalise the trajectory, and launch within a narrow window, or you miss your chance. It requires a level of coordination and bureaucratic agility that space agencies aren't traditionally known for. But it's not impossible. In 2005, NASA's Deep Impact mission was designed, built, and launched in just 3 years to smash a projectile into Comet Tempel 1. If we can move that fast for a solar system comet, we can move that fast for an interstellar one, especially if the spacecraft is already built and waiting. The European Space Agency has proposed a mission concept called Comet Interceptor, scheduled to launch in 2029. It's designed to sit at a gravitationally stable point in space, waiting for a pristine long-period comet or interstellar object to be detected, then redirect itself to intercept the target. If Comet Interceptor succeeds, it will be the first mission ever to visit an object from beyond our solar system. Imagine the data not just remote spectroscopy, but up-close imagery of the nucleus, direct sampling of the COMA, thermal measurements of the surface. We'd know exactly what an interstellar comet is made of, layer by layer. And then there's the dream scenario, a sample return mission. Bring back a piece of an interstellar comet to Earth, where it can be analysed in laboratories with instruments far more sensitive than anything we can launch into space. You'd have pristine ice from another star system sitting in a clean room, being picked apart molecule by molecule, isotope by isotope. That's the holy grail of interstellar object science, Doctor. Carey Liss from Johns Hopkins Applied Physics Laboratory explained. A sample return would answer questions we don't even know to ask yet. Right now, we're limited by what we can observe remotely, but if we had physical material in hand, we could do carbon dating, crystallography, amino acid sequencing analyses that require microscopic examination. We'd learn things about that comet's history that spectroscopy alone could never reveal. Here's the exciting part: the more interstellar objects we detect, the better our chances of catching one early enough to launch a mission. If Rubin finds 10 per year, and even one of those has a trajectory favourable for interception, that's a launchable target every decade, and over time we'll build a catalogue interstellar objects from different parts of the galaxy, with different chemistries, different isotopes, different stories. We'll start to see patterns. Maybe comets from one region of the galaxy are consistently carbon-rich. Maybe another region produces water-rich comets. Maybe we'll find objects that don't fit any category we've imagined, forcing us to rethink how planetary systems form entirely. But the biggest question hanging over all of this is how common are these objects? Really, right now, estimates vary wildly. Some models suggest there's one interstellar object larger than 100 meters passing through our solar system at any given moment. Other models say it's more like 10 Doctor. Avi Loeb's calculations, based on Oumuamua's discovery, suggest the galaxy contains 10 quadrillion interstellar objects, a number so large it's almost incomprehensible. If those estimates are correct, then interstellar space isn't empty. It's crowded. Every cubic light year contains thousands of wandering comets and asteroids, each one a silent witness to the chaos that birthed it. And if that's true, then the galaxy isn't just a collection of isolated star systems. It's a web of shared material, constantly exchanging debris, constantly mixing chemistry, constantly linking distant worlds through the objects they eject. You realise what that means. Write 3i/Atlas isn't just teaching us about one alien solar system, it's teaching us that the galaxy is connected in ways we never imagined. And the more objects we find, the clearer that picture becomes. But there's one piece of the puzzle we haven't fully addressed yet. What does 3i/Atlas tell us about the star that made it? Stars are element factories. Every atom heavier than hydrogen and helium, the carbon in your body, the oxygen you breathe, the iron in your blood was forged inside a star. And when you analyse the chemistry of something like 3i/Atlas, you're not just learning about the comet, you're learning about the star that made the atoms it's built from. You're reading the biography of a sun you'll never see. Let's start with the basics. Stars create elements through nuclear fusion. In their cores, hydrogen atoms slam together under immense pressure and temperature. Fusing into helium and releasing energy, that's what makes stars shine. But as a star ages, it starts fusing heavier elements, helium into carbon, carbon into oxygen, oxygen into neon, and so on, building up the periodic table one fusion reaction at a time. When massive stars finally explode as supernovae, they scatter those elements into space, enriching the surrounding gas clouds with heavy elements that eventually get incorporated into new stars, new planets, and new comets. This process is called stellar nucleosynthesis, and it leaves fingerprints. The ratio of heavy elements to lighter ones, what astronomers call metallicity, tells you how many generations of stars lived and died before your star was born. A star with high metallicity formed from gas that had been enriched by many previous supernovae. A star with low metallicity formed from more pristine gas, closer to the composition of the early universe. Now, here's the fascinating part. You can infer a star's metallicity by analysing the material that formed around it. And that's exactly what scientists are doing with 3I/Atelas. Remember those elevated levels of carbon-13 and oxygen-18 we talked about earlier? Those isotopes are created inside massive stars through nuclear burning processes, then ejected into space when those stars explode. The fact that 3I/Atlas shows higher than solar ratios of these isotopes suggests its parent star formed in a region of the galaxy that had been seeded by more supernovae than the neighbourhood where our sun was born. Dr. Ewan van Dyshoek from Leiden University, an expert in astrochemistry, explained it this way. When you measure isotopic ratios in a comet, you're essentially measuring the chemical heritage of its birth cloud. High carbon, 13 and oxygen, 18. That tells you the star formed in a chemically evolved environment, likely closer to the galactic centre, or in a dense star-forming region where supernovae are more frequent. Let's dig deeper. The Milky Way has a metallicity gradient. Stars near the galactic centre are generally richer in heavy elements, because that's where star formation has been most active over billions of years. Stars in the outer spiral arms, like our Sun, have lower metallicity because they formed in less enriched environments. If 3I/Atlas's isotopic signatures suggest higher metallicity than solar values, that could mean its star formed closer to the galactic centre, maybe 15,000 to 20,000 light-years from the centre, compared to our Sun's 26,000 light-years. But there's another possibility. The star could be younger than the Sun. Our Sun is 4.6 billion years old, which makes it a middle-aged star. But if 3I/Atlas came from a star that's only 2 or 3 billion years old, it would have formed from gas that had been enriched by billions of additional years of stellar evolution. Younger stars naturally have higher metallicity because the galaxy has had more time to build up heavy elements. The problem, we have no way to directly measure the age of 3I/Atlas's parent star. We can only infer it from the chemistry. Now let's talk about something even more specific, sulfur. Sulfur is fascinating because it's produced almost exclusively in massive stars at least 8 times more massive than the Sun through a process called oxygen burning in the final stages before supernova. When these stars explode, they flood the surrounding space with sulfur. So when scientists detected elevated sulfur levels in 3I/Atelas's COMA, it raised a question: was its parent star particularly massive? Or did it form near a massive star that had recently exploded? Dr. Ted Bergen from the University of Michigan said, "Sulfur abundance is a tracer of violent star formation environments. If you see a lot of sulfur, it means massive stars, the kind that burn bright and die young, were nearby." 3I/Atlas might have formed in a stellar nursery where O-type and B-type stars were common, flooding the region with heavy elements before blowing themselves apart. This matters because massive stars don't just enrich their surroundings chemically, they also shape the dynamics of planet formation. Their intense radiation and stellar winds compress nearby gas clouds, triggering the collapse that forms new stars, but they also disrupt protoplanetary disks, blowing away lighter elements and leaving behind heavier, more refractory materials. If 3I/Atlas formed in such an environment, that could explain why its carbon-to-oxygen ratio is so high. The lighter oxygen-rich molecules might have been preferentially blown away, leaving behind a carbon-enriched disk. But here's where it gets even more interesting. The presence of certain molecules in 3I/Atelus's COMA can tell us about the temperature and luminosity of its parent star. Remember the ethane and methanol we detected? Those molecules require UV radiation to form. The more UV light flooding a protoplanetary disk, the more complex hydrocarbons you get. And UV output depends directly on the star's surface temperature. Our Sun is a G-type star with a surface temperature around 5800 Kelvin. But if 3I/Atlas came from an F-type star just one spectral class hotter, with temperatures around 6500 to 7500 Kelvin, the star would emit significantly more UV radiation. That extra UV could drive the hydrocarbon chemistry we're seeing in the COMA. Alternatively, the star could have been cooler a K-type or M-type star, but compensated by having a more active stellar surface. With frequent flares pumping out bursts of UV light, Dr. Kevin France from the University of Colorado, who studies stellar UV radiation, noted. The hydrocarbon abundance in 3I/Atlas is consistent with formation around a star that's slightly hotter and more luminous than the Sun, or alternatively, a cooler star with high magnetic activity. Both scenarios work. We just can't tell which one is correct without more data. And then there's the nitrogen mystery. The high ammonia levels we detected suggest nitrogen was abundant in the protoplanetary disk. But nitrogen is tricky. It's mostly produced in intermediate mass stars between 1, 5 and 8 solar masses through the CNO cycle, a set of fusion reactions that convert carbon, nitrogen, and oxygen into each other. If 3I/Atlas's parent star had high nitrogen abundance, it might have formed from gas enriched by intermediate mass stars that had evolved into red giants and shed their outer layers, spreading nitrogen-rich material into space. This paints a picture 3I/Atlas likely came from a star that formed in a chemically rich, dynamically active region of the galaxy, a place where massive stars exploded, intermediate mass stars shed their envelopes, and UV radiation sculpted the chemistry of emerging planetary systems, a place where planets and comets formed quickly, violently, and with compositions that differ noticeably from what we see in our own solar system. But here's the haunting part: we don't know if that star is still alive. Stars more massive than about 8 solar masses live fast and die young lifespans measured in millions of years, not billions. If 3I/Atlas formed around a massive star, that star might have already exploded as a supernova long before the comet reached us. The system that birthed this comet might not even exist anymore. Dr. Barbara Ercolano from Ludwig Maximilian University of Munich put it poetically. Every interstellar comet is an orphan. It left home billions of years ago, and by the time it arrives here, there's a very real chance its parent star is already dead. We're studying ghosts' remnants of stellar systems that may have vanished while the comet was still crossing the void. Or, and this is equally possible, the star is still out there, shining quietly in some distant corner of the galaxy, surrounded by planets we've never detected. Possibly even planets where life has taken hold. 3I/Atlas carries the chemical signature of that star's richness in heavy elements, its abundance of carbon and nitrogen, its production of complex molecules. If those same elements were present in the rocky planets of that system, if nitrogen and carbon were available in abundance, then the building blocks of life were there too. Which brings us to the final, most profound question, could 3I/Atlas be carrying more than just chemistry? Life needs three things: liquid water, energy, and organic molecules. And 3I/Atlas has at least two of them frozen in its water, obviously detected in abundance in its COMA, and organics hydrogen cyanide, methanol, formaldehyde, ethane molecules that, under the right conditions, can link together to form amino acids, the building blocks of proteins. The question isn't whether 3I/Atlas carries the ingredients for life. The question is, could it carry life itself? Let's be clear, no one is claiming 3I/Atlas is harbouring alien microbes, but the possibility isn't as far-fetched as it sounds. Here's why. We know that microorganisms on Earth can survive in extreme environments buried miles beneath Antarctic ice, thriving in boiling hydrothermal vents, enduring lethal doses of radiation in nuclear reactors. Some bacteria can enter a dormant state called sporulation, where they essentially shut down all metabolic activity and become nearly indestructible. In this state, they can survive for thousands, possibly millions of years, waiting for conditions to improve. In 2000, scientists revived bacteria from a 250-million-year-old salt crystal. In 2020, microbes were brought back to life from sediment cores buried 100 million years beneath the Pacific Ocean floor. If life on Earth can endure that long in dormancy, could it survive a journey through interstellar space? Frozen in a comet's ice doctor, Gerda Horneck, a pioneer in astrobiology who studied the survival of organisms in space, conducted experiments aboard the International Space Station exposing bacteria, fungi, and even tardigrades, those microscopic water bears, to the vacuum of space. Intense radiation and extreme temperature fluctuations. Some survived. Not all, but some, she concluded. Life is far more resilient than we ever imagined. If microorganisms were embedded deep within a comet's ice, shielded from radiation by meters of frozen material, they could theoretically survive interstellar transit. Now think about 3I/Atlas. It's been frozen at temperatures near absolute zero for potentially millions of years. Cosmic rays have bombarded its surface, yes, but only the outer layers. Anything buried just a few meters deep would be protected. And when the comet entered our solar system and began to warm, that ice started sublimating, releasing gas and potentially whatever was trapped inside. This is the core idea behind Panspermia, the hypothesis that life didn't originate independently on every planet, but rather spreads through the galaxy via comets, asteroids, and interstellar debris. It's controversial, but not fringe. Scientists like the late Fred Hoyle and Chandra Wickramasinghe argued for decades that comets could seed planets with organic material, or even with dormant microorganisms, jump-starting life, wherever conditions allowed. Here's the evidence in favour. First, we know comets delivered water and organics to early Earth. The late heavy bombardment 4 billion years ago wasn't just violent, it was also fertile, bringing the raw materials necessary for life. Second, we've detected amino acids in meteorites. The Murchison meteorite, which fell in Australia in 1969, contained over 70 different amino acids, including some that are used by life on Earth. If meteorites carry amino acids, why not comets? And if comets carry amino acids, why not the precursors to life itself, Doctor? Sandra Pizzarello from Arizona State University, who analysed the Murchison meteorite, said, "Organic chemistry in space is far more complex than we thought. We're finding molecules that are 1 or 2 steps away from becoming biologically relevant. The line between chemistry and biology is blurrier than it appears." Now, let's talk about what 3I/Atlas could mean for habitability in its home system. If the comet carries organic molecules, and we know it does, then those molecules were present in the protoplanetary disk where planets formed. Any rocky planets in that system would have been bombarded by similar comets early in their history, just like Earth was. And if those planets had liquid water, stable climates, and protective atmospheres, those organic molecules could have evolved into life. The carbon to oxygen ratio we measured, remember, around 0.9, much higher than Earth's, could actually favour the emergence of life. Carbon is the backbone of organic chemistry. More carbon means more potential for complex molecules to form. Dr. Natalie Batala from UC Santa Cruz, who studies exoplanet atmospheres, noted, carbon-rich planets might have very different biochemistry than Earth, but that doesn't make them less habitable. In fact, a high CO ratio could lead to richer organic chemistry, more diverse prebiotic molecules, and possibly faster pathways to life. But here's the flip side. High carbon also means different planetary compositions. Earth is a silicate planet. Our crust is made of silicon and oxygen. But in a carbon-rich system, rocky planets might have crusts made of graphite or silicon carbide instead. Their atmospheres might be dominated by carbon monoxide and methane rather than nitrogen and oxygen. Life there, if it exists, would look nothing like life here. And that brings us back to 3I/Atlas as a messenger, even if it doesn't carry life, is carrying information about whether life could exist in its home system. The presence of nitrogen-rich compounds like ammonia suggests nitrogen was available essential for DNA and proteins. The presence of water ice confirms that H2O existed in the outer disk, which means it could have been delivered to inner planets. The detection of sulfur compounds means another key biogenic element was present. All the pieces are there. Dr. Sarah Seeger from MIT, who specializes in biosignatures, said, "When we search for life on exoplanets, we look for atmospheric signatures, oxygen, methane, phosphine molecules that might indicate biological activity. But we're searching blindly because we don't know what those planets are actually made of. Interstellar comets give us ground truth. They tell us this is what was available in that system. These are the building blocks. Now we can make better guesses about what kind of life might emerge there." Let's take this one step further. If interstellar comets are common, and we think they are, then organic material is being exchanged between star systems constantly. A comet ejected from one system could, in theory, crash into a planet in another system millions of years later, delivering its cargo of water, organics, and possibly even dormant microbes over billions of years. This process could link entire regions of the galaxy biologically, creating a web of shared chemistry, or even shared life. Some scientists take this idea seriously. Dr. Edward Belbruno from Princeton University calculated the probability of panspermia between neighbouring star systems and found it's not negligible. He said, "If life arose in one system and spread via comets, it could colonize dozens of nearby systems within a few 100 million years. From there, it spreads exponentially. Life wouldn't be a rare accident confined to single planets, it would be a galactic phenomenon." Does that mean 3I/Atlas is carrying life? Almost certainly not. The odds are astronomically low. But does it mean life could exist in the system 3I/Atlas came from? That's a very different question. And the answer, based on the chemistry we've detected, is yes. It could. The ingredients are there. The conditions seem plausible. Whether life actually arose, whether it's still there, we have no way of knowing. Not yet. But here's what we do know. 3I/Atlas is more than a comet. It's a time capsule, a chemical archive, a witness to the formation of an alien solar system billions of years ago and billions of miles away. Every molecule in its COMA is a word in a story we're only beginning to read. A story about how stars make elements, how planets form from chaos, how chemistry becomes complexity. And maybe, just maybe, how complexity becomes life. And the most incredible part, this is just the beginning. 3I/Atlas is one comet, one visitor, one data point. But dozens more are coming. Each one will tell a different story. Each one will reveal a different system. And together, they'll show us something we've never seen before: the galaxy itself, not as a collection of isolated stars, but as a living, breathing, interconnected web of chemistry, material, and possibility. Every comet is a messenger. Every coma is a diary. And 3I/Atlas just delivered the first page.